In the last presentation, we explored the von Neumann architecture and looked at how we could write programs for a machine, with no tools or programs to help the user. Instructions and data had to be encoded in binary. We also had to keep track of a lot of registers, such as the program counter, the instruction register, the memory data register, and the memory address register. This was in addition to the ones we used to hold data. I think you'll agree that it was a pretty miserable experience. To make this better, one of the first things early computer scientists did was to make system software. System software is a collection of programs that help us to manage resources of the computer and to serve as an intermediary between the user and the hardware. One of the major pieces of system software is the operating system. This piece of software performs tasks previously assigned to the computer operator. The operating system provides an interface for the user to interact with the machine. It also acts as a receptionist and a dispatcher for information. It schedules programs, provides security, and works to provide efficient allocation of resources. You'll see a lot more about operating systems in your studies in computer science. In addition to the operating system, there is a host of other system software. Language services support high-level languages, memory managers allocate memory to programs, information managers organize mass storage, the scheduler manages programs that are waiting to run, and there are a collection of utilities, tools, and program libraries and text editors. Assembly language was the first attempt at improving the programming experience. It still used the underlying machine language, but it provided opcodes for the commands. So instead of having to remember that 0000 was the load command, you could simply write the word load. Assembly language also had provisions for providing symbolic addresses for instructions and data. So instead of loading from location 000000001001, you could simply load the variable A. You could also label instructions to denote subroutines in the beginning and ending of control structures. Assembly language also provided pseudoops to generate data so that you didn't have to recall the variable A is stored at location 101100111011. Associated system software also assists with memory management, so you didn't need to think about where you were putting things in memory. While writing code in assembly language today may seem horrifying, it represented a significant step over using machine language to write programs. In fact, we usually denote machine languages as first-generation programming languages, with assembly languages being the second generation. Hence, they were a significant advancement. You're probably familiar with third-generation programming languages such as Java, C++, and Python that are much more machine-independent and programmer-friendly. Assembly language probably seems a bit dated, but there are still uses for it today. One of the main areas is in embedded real-time systems that have constraints on their speed and size. Consider a flight navigation system, a robotic device on Mars, or a medical device inside a patient. The computational components of these devices have limited capabilities and can be extremely difficult to upgrade their hardware, if not impossible. Programming these devices in assembly language allows us to optimize for memory and speed constraints. Assembly language is also used in device drivers and interrupt handlers, since this code needs to interact directly with hardware. It's also useful in legacy systems that still run on IBM mainframe computers. It also has some uses in high-performance computing applications, and finally it's often used to provide security, for example avoiding timing attacks, or to bypass security, for example writing viruses. Assembly language also helps us to understand the underlying operations involved in numerical computations made using third-generation programming languages. For example, long operations such as multiplication and division. It's also necessary for understanding how to write compilers. While not as omnipresent as it was in the 1960s, assembly language programming can still be an important skill for today, and it can help you to differentiate your resume. This is an example of the assembly language command from the Schneider and Gersing text. It's worth noting that assembly languages are machine-specific, so different assembly languages will have different formats. In this example, the instructions start with an optional label, symbolic address, followed by an opcode and address fields. At the end, there is an option to insert a comment after 2 dashes. And you can see the example with next step, load X, and that puts X into the register R. In this table, we see the assembly language from the Schneider and Gersing text. As we mentioned previously, there's one-to-one correspondence between the assembly language instruction set and the underlying machine instruction set. In fact, you can see the binary opcode right next to the assembly instruction in this table. In addition to assembly language instructions, assembly languages have something known as pseudoops. Pseudoops are commands in the program directed to the assembler, but they are not converted to machine instructions. .begin and .end are used to mark where the instructions are located, and .data is used to mark memory location as holding data. Data are located after the halt instruction, but before the .end pseudo-op. This is an example program fragment for calculating x is equal to y plus 3. We load y, add the value at location 3, and store the result in x. We also see the symbolic data addresses and the pseudo-ops used to generate the data at the end of the program. You can see that this takes more commands than what we would have in the third generation programming language. That's known as the instruction explosion. This is another example fragment. In this fragment we get input values for a and b. While a is less than b, we output a and then subtract 2 from the value of a. You can see the labels as symbolic addresses to start and end the loop. As with our previous example, we locate the data after the halt instruction, but before the .end pseudo-op. The assembly language process begins with the programmer creating a source program in assembly language. The assembler translates the source program to an object program in machine language. The loader places the object program in memory, and the hardware runs the object program. The assembler translates the assembly language to machine language. To do this, it converts the symbolic opcodes to their binary equivalents and converts the symbolic labels to memory addresses. It also performs the pseudo operations such as generating data. Finally, the assembler produces the object file containing machine instructions for the program. To convert symbolic opcodes to binary opcodes, the assembler maintains a table where it looks up the symbolic opcodes and substitutes the binary analog. The assembler uses binary search to optimize table lookups, and the assembler needs to look over the code 2 times. The instructions from the start of the program. It also collects symbolic labels and adds them to the symbol table along with the location counter. The second pass looks up and replaces the opcodes. It also substitutes label references with locations from the symbol table and sets up the .data pseudo-ops with location binary values. Finally, the assembler writes instructions to the object file as part of this pass. The loader then gets the program ready to run. It places instructions in memory and triggers the hardware to run the program. Thanks so much for watching as we approach the end of